Good day. So this recorded lecture, is to replace the missed lecture that should have occurred on January 17th due to snow. My name is Eric Ferrand, and what I want to do is take our discussion about perturbations a little further by considering the example of a car which we are asked to follow a certain velocity. And unlike the initial situation we discussed, the car is subject to not only some nominal behavior, which is basically a direct function of the throttle, but also subject to perturbations, where the perturbation could be a mix of the headwind and what I would call the effects of gravity. So, taking things from there, what we are interested in is looking at the effect of a feedback loop on this specific system. So here's the date. The feedback loop we are building is the same as before. That is, the control system measures the error in speed between what I would call the desired speed on the one hand and the measured speed on the other hand. Okay, so the desired speed is named SD and the measured speed is named S. Now, what we have is, unlike the previous example, there was no perturbations. What we see happening is the following. So, in a block diagram way, so we're still looking for a controller. We're going to use a simple gain K here. And the single gain K will produce the throttle input, just like before. However, things are a little bit different in terms of the effect on the car. There is what I would call the nominal car effect. Let me redraw this. So as I said, this is the nominal car effect here. Okay, so that's the nominal dynamics, but to it, what we see is that we add the perturbation W. Okay, so if you will, the nominal car behavior is here, and the perturbation W comes here, and the sum of the two create the speed. So it's as if we said that there was a little additive term here. You have to get used to these pluses and these pluses or minuses that sort of help us draw the effect of the different inputs into a system using a circuit-like representation. So the system we have is really something like this now. So on the one hand, you have the regular information that we have already seen, the reference speed, the throttle, and the actual speed of the car. But on top of that, you have now this element W, which we tend to call a disturbance. And the question is, what is the effect of the feedback control architecture on this disturbance? So for that, we set the same equations as we have set before, properly modifying it to account for the presence of the disturbance W. So we write that S is equal to, um, let's see, so the nominal car output, we haven't given it a name yet, but maybe we could call it O. So S would be equal to O plus W. Now, O is equal to, in the notation that we have chosen, here it will be exactly this, H inverse L of the throttle. So it's a function of the throttle setting. Okay, so I'm going to add it here, like this. Okay, and then we write that throttle is equal to K times SD minus S, like we have derived before. Okay, and this comes from this part of the loop in such a way that eventually we obtain that S is equal to H inverse of L of throttle plus W, or S is equal to H inverse of L of K times SD minus S plus W. Okay, so this is a little bit of a complicated equation, but uh, its essence nevertheless appears here, which is that um, the function H inverse times L for a usual car just is monotonic and grows to infinity. It is basically the effect of the throttle on the car speed short of the perturbation W. So what happens when I make K big? Okay, what happens when I make K big is that if SD is different from S, then, so the speed is different from the desired speed, then K times SD minus S will become big, okay? But if it is big, then H inverse L K times SD minus S will become big as well. But if this is the case, then H inverse L K times SD minus S minus W or plus W, which is also equal to S, will become big. So let us make this slightly more quantitative. Let's say that S is less than SD, then uh, KSD minus S becomes big and positive, which makes this thing big and positive, which makes S big and positive. So, but if S is big, then it could become that S becomes greater than SD, and therefore this is impossible. So when K is big, then SD minus S must be small. No matter what, no matter what, uh, W, by the way. So what can we conclude is that the impact of a large feedback gain is still a small error in speed. And that is true even when we have a perturbation W, which is a mix of aerodynamics and slope changes. Okay, so what we have here is a fairly complex uh, architecture. Actually, not very complex. It's as a matter of fact pretty simple. Okay, and that pretty simple architecture, feedback control architecture, is actually capable of taking care of W. So you have what's called a proper disturbance rejection. Okay. Now let's look at some simpler case. So far we have used arbitrary car behaviors. Sometimes we can use simpler things. For example, what if the nominal relationship between the throttle and the car speed were simply speed is equal to a coefficient k, small k, times the throttle. Okay. Then things could get a lot simpler. We could write that so that's for the nominal. There are no perturbations. If you have perturbations, then you get speed is equal to k times throttle plus a perturbation w. Okay, so that's with perturbations. Then we can write that the feedback loop works as follows. On the one hand, we have indeed S is equal to K times throttle, which I would call T, plus W. On the other hand, the error is equal to SD minus S. On the other hand, um, throttle setting is equal to K, a big K, my mistake, large K times R, which gives us the equation S equals KT plus W, and then T is equal to K times SD minus S, which gives us the equation S is equal to K times K times SD minus S plus W. We can then write an explicit expression for S, which should be like S times 1 plus big K times small k is equal to big K times small k SD plus W, or S is equal to K times small k divided by 1 plus K times small k SD plus W divided by 1 plus big K times small k. So things become extremely quantitative at this point. Indeed, we have an explicit expression for S, and that explicit expression tells us that when K gets big, then on the one hand, this term tends towards 1. On the other hand, that term tends towards 0, which means that when K is big, you get S is equal to about equal to SD plus W divided by infinity, which is about 0. In other terms, you have indeed good disturbance rejection. Okay, the disturbance is rejected, and the nominal and desired speed is properly followed. So the command is followed. So this would be great. And lots of people might think, well, uh, why not? Uh, uh, why not using a large K all the time? So should we use a large K all the time? Indeed, it looks like it's a good recipe to take care of perturbations and make sure our car follows the required speed regardless of what happens around it. It is time to introduce another problem, which is what we call sensor error or sensor perturbations. So what are the sensor perturbations? Well, it is the fact that although the car may be going at a certain speed, when it goes to the sensor, you may actually measure speed plus a small quantity v. Okay, so that's called sensor noise. Okay, enter in a block diagram way. The way it enters into the system is that while we have the car here, and I will avoid uh, the input of perturbations directly on the car and instead directly produce the speed s. Okay, so we temporarily forget about the process noise that we have seen before. What happens is that in the feedback loop, the sensor produces S plus W. Another way of capturing this is to say that what goes into the controller is sensor plus V, okay, and that enters the feedback loop and the comparison with the desired speed SD. And that feeds into our controller that then produces the throttle T, okay? So what you see is that the sensor noise can be measured as something that enters the feedback loop, typically where I have shown it, okay? Now, what is the effect of feedback on that noise, on that sensor noise? Or to be more precise, let's look at the effect of the sensor noise on feedback. Well, I can still introduce my different quantities. I have S is equal to, let's simplify things and say it's going to be proportional to T. Okay? Now, K is equal, sorry, T is equal to K times R, that is SD, minus what? Well, minus this quantity here, which we're going to call S sensor, like this. Then S sensor is equal to S plus V, the small sensor noise. Once we put everything together, we obtain that S is equal to KT and T is equal to K times SD minus S minus V. Eliminating T from the equation gives us S is equal to, oh, I made a small mistake here. This is not a big K, this is a small k. So I write S is equal to K times T, which is big K, times SD minus S minus V. And therefore, putting S on the left side, all terms in S on the left side get that S times 1 plus small k times big K is equal to small k times big K times SD minus small k times big K times V. Or in other terms, S is equal to small k times big K divided by 1 plus small k times big K SD minus small k times big K divided by 1 plus small k times big K V. And as k grows to infinity, we obtain that S is equal exactly to SD minus V. In other terms, we have this persistent error that's due to the sensor and that we cannot get rid of with large K. In fact, the good way to get rid of V, sorry, is to use a small k. Yes, because small k, big K divided by 1 plus small k times big K tends towards 0 when big K tends towards 0. Okay? The problem is that we do not do good tracking of SD, because if we make big K small, then this term also becomes small. So summarizing, for what I would call process disturbance, or noise, that is effect of slope, uh, aerodynamics, K big is good, but to take care of noise disturbance, sorry, I meant sensor disturbance or noise, then K small is good. How can K be big and small at the same time? That is one of the key questions that we will address throughout this course. And what we will see is that instead of using K, a number, we use K, a function. And the choice of big and small will depend on frequency. But I don't want to tell you more at this point. You should just remember that what we need in order for our feedback thing to work well is, on the one hand, a large gain to get rid of what I call process noise. On the other hand, a small gain in order to get rid of sensor noise. This apparent contradiction will be solved throughout this course by working with objects that are just more sophisticated than K merely being a number. Instead, K will be chosen to be a function, and to be more precise, it will be chosen to be a dynamical system. You will see this later throughout this semester. Thank you.